If you fell into a black hole, you wouldn't explode. You wouldn't vanish instantly. And the strangest part is this: you might not even notice the exact moment when escape becomes impossible. From your point of view, it could feel almost normal. But from the outside, the universe would watch you slow down, freeze, and fade away forever. So today, let's do something terrifying and fascinating. Let's follow the journey, step by step, all the way down. A black hole is not an empty hole in space. It's an object with so much mass packed into such a tiny region that gravity becomes overwhelming. Gravity is the force that pulls objects toward each other. On Earth, it keeps your feet on the ground. But in space, gravity does something deeper. It bends space and it bends time. Together, we call that space-time. Imagine space-time as a stretched sheet. A planet makes a small dent. A star makes a deep dent. A black hole doesn't just dent the sheet. It creates a slope so steep that everything slides inward. Most black holes form when massive stars die. A huge star runs out of fuel. The outward pressure that kept it stable collapses, and gravity wins. The star implodes, compressing more mass than you can imagine into a region smaller than a city. That's the birth of a stellar mass black hole. And in the centers of galaxies, we find supermassive black holes, millions or billions of times the mass of the sun. Around every black hole is an invisible boundary. It's called the event horizon. This is the line you can cross, but never return from. Not because there's a wall, but because beyond that line, the escape velocity becomes greater than the speed of light, and nothing can go faster than light. That's why black holes are black. They don't reflect light. They don't emit light. Anything that crosses the event horizon is cut off from the rest of the universe forever. Now here's something important. A black hole is not just darkness. The space around it can be incredibly bright. Many black holes have a swirling disk of superheated gas around them. This is called an accretion disk. Matter spirals in, speeds up, collides, heats up, and can glow hotter than the surface of stars. So the area around a black hole can be a blazing furnace, while the black hole itself remains invisible. As you approach a black hole, something very strange happens to light. Light itself can bend into curved paths, and near a black hole, light can even orbit. There's a region where this becomes possible, sometimes described as the photon sphere. If you were hovering near that region and looked around, you could see something impossible. You could see the back of your own head, because light leaving your back could curve around the black hole and return to your eyes. The universe becomes a cosmic funhouse mirror. Stars appear warped. Galaxies stretch into rings. Your sense of direction starts to collapse. And the closer you get, the smaller the safe sky becomes, as more and more light paths get trapped. Near a black hole, gravity doesn't just bend space, it bends time. The stronger the gravity, the slower time passes for you compared to someone far away. This is time dilation, and it gets extreme near a black hole. From your perspective, your heartbeat feels normal. Your thoughts feel normal. But if you could look back at the universe, you might see it racing forward. Distant stars changing, galaxies drifting, the sky evolving. From far away, someone watching you fall would see something different. They would see you slow down, more and more. As you approach the event horizon, your signals take longer to reach them. Your light becomes stretched, redder, dimmer, until you fade into the darkness. To them, you never quite cross. You just freeze, and disappear. But for you, you keep falling. Now let's talk about the danger that isn't heat. It's the difference in gravity across your body. Your feet are closer to the black hole than your head, so your feet are pulled harder. That difference is called a tidal force, and tidal forces can stretch objects violently. This is where the word spaghettification comes from. You get pulled longer, thinner, as the gradient of gravity increases. But here's a twist. For small black holes, tidal forces near the horizon are extreme. You'd be stretched apart quickly. For supermassive black holes, the event horizon is so large that tidal forces at the horizon can be relatively gentle. In that case, you might cross the event horizon intact, at least at first. But don't celebrate, because inside everything gets worse. Gravity keeps rising, and eventually tidal forces win. Once you're inside the event horizon, space and time lose their normal meaning. There is no turnaround. There is no sideways escape. Every possible path forward leads deeper inward. Think of it like this. Outside a black hole, the center is a place you can move toward or away from. Inside the horizon, the center becomes your future, not a direction, a destination. No matter what you do, every second that passes takes you closer. And at the center lies the singularity, a region where our equations predict infinite density and infinite curvature of space-time. That's the point where our physics breaks. It doesn't mean we understand it. It means we don't. In reality, almost all black holes spin. They're born from spinning star, so they inherit that rotation. And when a black hole spins, it drags space itself around with it. This effect is sometimes called frame dragging. Near a spinning black hole, space-time behaves like a swirling current. You don't just fall, you get twisted. You get pulled into motion you can't resist. The faster the spin, the stranger the geometry becomes. Spinning black holes are not simple trapdoors. They are rotating storms in the fabric of reality. Now, for one of the strangest ideas in modern physics, black holes may not last forever. They can lose energy, very slowly, through a process called Hawking radiation. The basic idea is this: even empty space is not truly empty. Quantum physics suggests the vacuum seized with tiny fluctuations. Pairs of particles can briefly appear and disappear. Near the event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. And if it emits energy, it loses mass. Over unimaginable time spans, the black hole shrinks. And as it shrinks, the radiation becomes stronger, until in the far future, it may evaporate completely. A black hole with the mass of the sun would take around 10 to the power of 67 years to disappear. That number is so large it basically breaks the human brain. And supermassive black holes, even longer. So yes, black holes can die, but not in any way we can truly comprehend. So, what happens inside a black hole? We have theories, we have equations, but we do not have certainty because we can't see past the horizon. And our best physics doesn't fully describe what happens at the singularity. And that's not a failure. It's an invitation to keep questioning, to keep exploring, and to accept that the universe is far stranger than anything we can fully understand. Somewhere in the darkness, black holes are still waiting.